Okay, so here's what we were talking about last time. We were talking about how to do a change of basis for a linear transformation. Remember, what we've been doing is using bases as a convenient means of turning abstract things, like vectors, for example, into concrete, well, let's say numerical things, like lists of numbers, ordered in tuples, right? And then, so it occurred to us, well, same thing for linear transformations. That's an abstract thing, and clever use of bases, we can rewrite them as numerical things, namely matrices. So, just like we can do a change of basis for vectors, wouldn't it stand to reason we could do a change of basis for linear transformations? And we talked about the idea for this last time. This part of the diagram represents how you'd represent T with respect to one pair of bases. This face of the diagram represents how you'd represent the same transformation with respect to a different pair of bases. And looking then at the diagram that sort of consequently shows up down here at the bottom, not hard to persuade yourself that if you want to identify this matrix, well, it's a succession of three things that you can see right here on the diagram, like that, right? Okay, so we went through an example of this last time. I am going to say a couple of words about the next example. The example that we did last time, we had this given right here, and we asked the question of how would I identify what this matrix is, A, where 1, 3 goes to 2, 5, and 2, 5 goes to 1, 3. What you might say is a peculiarity of this example is, well, the vectors that are convenient for inputs happen to be the exact same two vectors as the vectors that are convenient for the outputs. Right? 1, 3, and 2, 5 are the input vectors. I know how to multiply A times 1, 3, and 2, 5. The outputs that I would like to write all of my outputs in terms of 1, 3, and 2, 5, because there they are. Right? So a complaint that you might make against this example is, okay, this seems only to be a method that works in that extremely unusual special case where the input basis and the output basis are the same. So all I want to point out with the next example is, you totally can deal with this in a different situation where the input and output vectors are totally different. So here, input vectors 1, 3, and 2, 5. Let's say. Notice now that my two output vectors are not the same two vectors. They're a couple of totally different vectors. Right? And there's a temptation to say, oh my gosh, well then what basis are we going to use? Good news, we don't have to pick a single basis. Right? We can write this matrix B with respect to any pair of bases that we want. So coming back over to here, right? When you're representing a linear transformation, you get to pick a basis for the domain and a potentially totally different basis for the target. So pick your basis domain based on, no pun intended, what was going to be convenient for your work in the domain. And then likewise, pick your target domain with the idea in mind of thinking about what's going to be convenient for what you're going to be doing in the target. All right, so let's go through the example here. So I've got here again that I want to find this matrix B. B is it represents some linear transformation with respect to the standard basis. What I want to understand is, what is this linear transformation? B is a numerical representation of it, but S is the thing. So let's understand S. Now, how am I going to understand S? Well, I can understand S first with respect to whatever basis, whatever pair of bases. Let's pick some really convenient bases. What would be a really convenient pair of bases to understand S with respect to? Well, whatever I pick for the input basis, right? Whatever I pick here, that basis, those vectors are going to have to go in to this S transformation. Right? So how about we pick the two vectors that I know how to put in to the S transformation. Let's pick 1, 3, and 2, 5. Seems like a reasonable choice. Right, now likewise, we get to pick whatever we want to be our target basis. What should this script W be? I get to pick any basis I want. Well, whatever I pick for my script W basis, I'm going to have to write these outputs in terms of that basis. What basis would it be really convenient to write these two vectors in terms of? These two vectors being W1 and W2. Right? Well, here's the thing. These two vectors here, 3, 2, and 4, 3, that's what I'm really going to have to write in terms of whatever I choose as my W1 and my W2. So if I make them W1 and W2, then again, life is good. Right? So how do I write S in terms of the standard basis? Oh, hey, whoa, slow down. Now I'm not sure about that. But how to write S in terms of this pair of bases? Script V for the input, script W for the outputs. That's easy. Right? Finding these columns. How do I find this first column? Well, that first column comes from understanding this equation. Right? What is S of the first input basis vector, V1? And said differently, S of V1, its coordinates with respect to script W are 1 and 0. Right, how do I write W1? As a linear combination of my very conveniently chosen W1 and W2. 1, 0. Then likewise, I'll let you guys think through the details, but this tells me my second column, 0, 1. Okay, so we try to understand something first. We understand the linear transformation first with respect to a basis that makes it easy. And then we find ourselves wanting to convert. We have here an understanding of S with respect to convenient bases. I want instead to understand S with respect to given bases. So I need to do a change of basis. And again, it's a change of basis is just like we have back here, the change of basis formula right there. Okay. And following that procedure, it's all over but the arithmetic, really. Let me clean this up. So that is what's in the middle. These two change of basis matrices are easy to write down. That one's just a direct transcription. This is an inverse of a really easy matrix. Right? Remember, we have a really easy way to write a change of basis matrix if you know the input vectors with respect to the output vectors. And when it's the other way around, you just invert the matrix. We talked about that last time. And then arithmetic and result. Okay, so there we go. Section 5.3 is so long. We've just finally finished it, and took us a whole week to do it. Right, it's all we've done for this, since this last homework assignment. So, as we discussed in the email, this section 5.3 is the only section assigned for homework for this week. Okay, new topic. This is going to seem like an entirely different conversation here at section 5.4, eigenvectors and eigenvalues. I just want to do a little bit of foreshadowing very quickly. It turns out that this idea we're going to present here, this idea of eigenvectors and eigenvalues, and the idea that we just got through talking about, namely how to represent linear transformations with respect to a basis and how do you do a change of basis. Totally different seeming ideas, and in important ways that we're not prepared to see yet, they're going to dovetail powerfully. Right? So that's just a little bit of foreshadowing. You can try to think in terms of how that might go, but don't stress. We'll lay all of that out for you when we get to section 5.5, a little bit later on. Okay. All right. Okay. So here's the big equation. This is what we're interested in when we're talking about eigenvectors and eigenvalues. given a matrix, sometimes this weird little coincidence happens. Sometimes that when you multiply it by a vector v, what you get is a multiple of that exact same vector v. Certainly this does not happen every time, right? Certainly, most of the time when you multiply a matrix times a vector, you get an unrelated vector. You certainly don't expect to just get a scalar times that vector. But sometimes you do. If you do, that vector is called an eigenvector. By the way, we require non-zero. I'll come back to that in a moment. But the vector is called an eigenvector, and the scalar is called the eigenvalue for that eigenvector. Okay. Like I say, it's hard to see at a glance why this would be interesting, but it's going to turn out to be a very powerful idea. Let me just remind you, one of the things we talked about at the beginning of the course, we have to sometimes get a certain amount of stuff done before we can start to see the value in it. This, combined with the idea of change of basis for linear transformations, is going to end up helping us solve differential equations. It really will. It's just hard to see that coming right now. Okay. All right. So this is what we're going to be talking about for the rest of today. By the way, a quick cultural point. There are other kinds of analogous situations. Sometimes instead of a matrix times a vector, sometimes you have a linear transformation acting on a vector. Maybe one that has not a finite dimensional domain. So you can't represent it as a matrix. Anyway, nevertheless, you could talk about the analogous sort of thing happening. Sometimes this comes up in other situations. In physics, for example, quantum mechanics, from a certain point of view, could be thought of as that you're looking for certain solutions to equations that really look a lot like that. They're kind of eigenvector equations, just with different kinds of objects involved. So anyway, they tend to take this prefix eigen in front of eigenvector here, in front of eigenvalue here, and just kind of stick that in front of other whatever. So you'll hear in physics they'll talk about quantum states as eigenstates, and certain functions that satisfy equations that look kind of like that, they'll call eigenfunctions. So anyway, when you hear something like that, eigen whatever, what they're saying is there's an equation kind of like this one, and that this is one of the solutions to that equation. Okay, that's just a cultural point. Quickly, coming back to, why do we require these vectors to be non-zero? Well, let's think about what would happen if we let v equal to 0, and the answer is the question becomes kind of ridiculous if you think about it. It's always going to work, right? Whatever matrix you have, multiply it by 0, you will get, guarantee, a scalar multiple of 0. Right? It's going to work. Furthermore, it would work no matter what value you plug in as your lambda. So the whole thing just becomes kind of silly. So in order to make the idea consistently meaningful, we don't allow 0. Okay. How do you find eigenvectors and eigenvalues? There's a mechanical process, algorithmic, I'll say, and that is, first notice that this equation we want to solve is equivalent to that equation. The idea is to think of, imagine that I put an identity matrix right in there. And you can see if you subtract that term on the right over to the left, then you have a minus lambda I multiplied by v. Why do we make this switch? How is this a win? Well, the second equation here has a nice feature, and that is, notice we are looking for vectors that when you multiply by a matrix give you 0. Let me say that a little bit differently. We're looking for vectors that are in the null space of that matrix. Or said in chapter 1 terms, we're looking for homogeneous solutions, and we know how to do those things. Okay. So the way we actually get this done, by the way, notice in our process of trying to find these eigenvectors, note we still actually don't know the eigenvalues either. So I don't actually know what to row reduce just yet. So clever argument to be made on that. How do I figure out what lambda is? Well, if there is an eigenvector, there is a non-trivial null space. That means that this matrix A minus lambda I has to be singular, and then refer back to that very long list of equivalent conditions that we wrote down at the end of chapter 2. And among those, A minus lambda I being singular, its determinant's equal to 0. And by the way, this determinant, as it turns out, not hard to see, this determinant is a great big polynomial. Right, if A is made up of a bunch of numbers, lambda I is going to have a bunch of lambdas in it. A minus lambda I then has a bunch of lambdas in it. When you take the determinant, you're going to multiply those elements by each other in this prescribed way. You're going to get a polynomial in lambda. Okay, so this thing, this determinant, we call that the characteristic polynomial. So the characteristic polynomial is the thing whose roots are the eigenvalues. That's the way to think about it. The characteristic polynomial has roots that are eigenvalues. Okay. How are we doing? Is everybody on board so far? Okay. By the way, once you know the eigenvalues, now we know what to row reduce, given an eigenvalue. Now I know that matrix, and I can find the eigenvectors just by, find the homogeneous solutions, find the null space, however you'd like to think about that. Okay. Let's get our hands dirty and do one. See all this happening. Okay, so let's look at that matrix. By the way, I stole this matrix right out of the book. I'm going to keep using this matrix a lot because there's going to be a lot of situations where we need to know eigenvalues and eigenvectors, and rather than going through a different calculation each time, it's going to be nice to just refer back to, okay, here's our matrix. We already know the eigenvectors and eigenvalues. So we'll be seeing a lot of this matrix. Step 1, how do we find the eigenvalues? Follow the rule. There's your characteristic polynomial. Notice that your matrix A, there's your matrix A. Subtracting lambda I. Well, that's just going to subtract lambda on the diagonal entries. So there's your A minus lambda I. Everybody on board? Questions? Okay. Got to take the determinant. The determinant, by the usual rule, is that which you can multiply out to collect terms to get that, which you can then factor to get that. And then remember, why are we interested in the characteristic polynomial? We're interested in the characteristic polynomial because the roots of the characteristic polynomial are our eigenvalues. And so from here, you can see exactly what the roots are. The roots are -1 and 4, so those are the two eigenvalues. And it's a pretty straight up algorithmic process. Sounds like everybody's okay with that. Any questions? Everybody happy? Okay. All right, let's find the eigenvectors. Well, now we have to find the eigenvectors one eigenvalue at a time. We will start with -1. Plug in lambda equals -1. And our A minus lambda I becomes that. Keep in mind, eigenvectors are in the null space of A minus lambda I. So we just need to, go through and row reduce this A minus lambda I. And, a bunch of details. You guys remember how to do row reductions, right? And what you'll find is that all of the null space vectors of A minus lambda I are there. Namely, it's all multiples of the vector 3, 2. So make sure you can do that row reduction. I know it's a flashback to chapter 1 a long time ago. Okay. Questions? Everybody okay? Okay, so I want to show you all a shortcut that I like. I think that the following shortcut, by the way, the book doesn't talk about it. I think this shortcut is very convenient. It'll save you a bunch of time, and it's also good practice in thinking about important ideas that we've talked about thus far in the course. So I'm going to show you how to write down this null space without doing a row reduction. And it seems a little too good to be true. Not that this is a hard row reduction, but still. Okay. So here's the idea. Well, let's think about this. Here's the equation we need to solve. We're looking for this null space. Let's look at this matrix, and let's ask innocently, what's the rank of that matrix? So, it's got to be some number. It's how many pivots are in the reduced echelon form of this matrix? And we're going to be able to answer that question by kind of process of elimination. In other words, the whole point of this is to avoid row reducing. I don't want to have to actually go through and row reduce. Let's just process of elimination figure it out. Well, here's the thing. This matrix, I know that matrix is singular. That matrix is A minus lambda I. The whole purpose of this strategy is that A minus lambda I will be singular if you have an eigenvector, therefore an eigenvalue. Right? So this matrix, the rank, can't be 2. All right. It also can't be 0. Let's think about that. What would the matrix look like if the rank were 0? That would mean the reduced echelon form had no pivots. That means that no row has a first non-zero entry. That means that the reduced echelon form would be all zeros, which would only be possible if the matrix itself were all zeros, which is obviously not the case. Right? So, process of elimination, the rank can't be 2, the rank can't be 0, therefore the rank of this matrix is 1. And I'm going to say, approximately speaking, no effort required, because these arguments are practically always apply, right? We know we're looking at an eigenvalue. 2 is out. Vast majority of the time, your matrix is not all zeros. So 0's out, right? So this argument's pretty much always going to work. Okay. Now, so what? How does that help us find a null space? Well, here's the thing. The rank nullity theorem. Y'all remember the rank nullity theorem? The dimension of the null space plus the dimension of the rank is equal to the number of columns in the matrix, right? N. Well, that means that the dimension of the null space is the total number of columns minus the rank. And therefore, this dimension of this null space we're looking for is 1 in this case. All right, now that still doesn't answer the question. And yet, notice how little work we've done so far. We've made a couple of process of elimination arguments that are always going to work. We've done a subtraction. Right? This is a really easy subtraction. And the conclusion that we've gotten is, however, extremely powerful. This null space that we are looking for, we now know it is one-dimensional. That's a mouthful. That's a tremendous amount of information. One-dimensional vector spaces have some really nice properties. For example, any non-zero vector is a basis. Right? Any non-zero vector. So, by our clever little argument here, what we have reduced our question to is not, do the row reduction, because thank God we have row reductions, because that's the only way that we know for sure we'll be able to get all of the actual solutions. No, now it's just find any solution by hook or by crook, and you're done. Right? So it's a very nice argument. And how you do find this one solution. How did I come up with that 3, 2 is a solution? Well, that's just mostly just being a wisecracker. I see the 2's and the 3's and the minus signs and 2's and 3's. Let's take the 2 and the 3 and multiply by 3 and 2 and make the minus sign, and hey, it worked. Right? And that kind of strategy is going to be very effective in these kinds of problems. Okay, so this is a great method. I want to encourage you all to do this on exams. You don't have to, but I do want to encourage it. Let me comment on what you need to do on an exam if you do choose to use this method. You do have to document your reasoning. You can't just write down your answer. What I would like, what did I just do? What I would like for you to write down to document your process of how to solve that system is just write down rank is 1, therefore dimension of the null space is 2 minus 1 equals 1, and therefore that. That's all you really have to write. Everything else that's on this page of notes was just to help, communicate your first-time experience through this argument. But if you understand this argument, then I think, noting these highlights is sufficient to document your thought process. Is everybody on board? Okay. All right. Okay, so that's the sort of the alternative. Keep in mind where we were. We had an eigenvalue of 0. That gave us this matrix. We needed to find the null space, and rather than do the row reduction to get this null space, we now have the option of using that argument on the next page. Okay. All right, and yet we have still only looked at this one eigenvalue. We do still need to look at the other eigenvalue. 4. Well, it's a very similar method. When lambda is equal to 4, when lambda is equal to 4, that's lambda. A minus lambda I becomes that matrix. Note again, we are looking for a null space of a 2 by 2 singular matrix, and the argument goes just as before. I'm not going to write it down. Let's just talk through it. This matrix, the rank can't be 2. We know it's singular. The rank can't be 0. It's obviously not all zeros. Therefore, the rank is 1. Therefore, the dimension of the null space is 2 minus 1, namely 1. We're looking for a one-dimensional vector space. I'm simply going to produce any vector that I can think of by hook or by crook that is in the null space and declare that to be a basis, and therefore all of the eigenvectors are simply multiples of it. And again, you look at this matrix, think about how to be a smart alecky, just kind of observe any null space vector that you can find. 1, -1 is very convenient, and you're done. Okay. All right. Okay. There's a little bit of terminology that I need to talk about here. How people talk about eigenvectors. Roughly speaking, what I'm going to be doing is justifying a certain kind of what I like to call math slang that people use. It's a sloppiness of speech that's technically not correct, but everybody says it, and it makes a lot of sense if you really think about it. So here it is. Let's ask the question now. How many eigenvectors did we just find here? And the answer, there's a temptation to say, well, I see the one eigenvector, but of course k can be any number, right? All multiples of 1, -1 are eigenvectors. We have in fact technically found infinitely many eigenvectors. Yeah? Okay. Here's the other thing though. That's always going to be the case. We're always going to find, the whole point, we know this matrix is singular. There's going to be at least a one-dimensional vector space of eigenvectors. There will therefore always be infinitely many. So this terminology, hey, how many eigenvectors did you find, is kind of wasted if the answer is always infinity, right? So there is, however, another interesting question that can pretty naturally be kind of connected to how many eigenvectors you find. And that is, how many eigenvectors are in a basis for what you found? Right? All null spaces have infinitely many vectors, but they have interestingly different numbers of bases. Right? So this is a one-dimensional null space, and therefore the basis, a basis for this vector space consists of one vector. So in common math slang, people routinely say, for this eigenvalue, we found one eigenvector. Everybody see what I'm talking about? So, interpreted literally, it's obviously false. You can't just find one. It's got to be infinitely. Okay, yeah. Obvious, and therefore, why are we going to bother ourselves, being burdened by that? People routinely say that we have found here one eigenvalue. One eigenvector. One eigenvector. Okay, so in that sense, and this is going to end up being convenient, for this eigenvalue of -1, we found kind of one eigenvector. For this eigenvalue of 4, we found, again, in math slang, one eigenvector. Grand total, we found 2 eigenvectors. Okay. Everybody on board? Okay. Okay, now I want to make an observation that I kind of glossed past earlier, and that is this choice of terminology. We call this the characteristic polynomial. Raises an eyebrow, if you think about it. That being, hey, didn't we already use that word? Right? We've already made a definition for something called a characteristic polynomial. It was back in chapter 4, right? And we were solving a certain category of differential equations, and we found that there was a certain polynomial whose roots allowed me to, by way of a certain algorithm, find all of the solutions that I was looking for. Okay. But it was for a differential equation. Here, we're in this totally different situation. There's not a differential equation in sight. We're now looking at matrices, and for some reason trying to find eigenvectors, but we again find ourselves in this circumstance where there's a certain polynomial whose roots, namely the eigenvalues, allow me to find the things that I'm kind of interested in, namely, in this case, the eigenvectors. Everybody see what we're talking about? There's kind of an analogy there. So we're going to use the term characteristic polynomial. Again, it seems like an abuse. Now we have 2 different things called characteristic polynomials. The good news is those 2 things are so entirely distinctly different, there's no confusion. Right? If I say characteristic polynomial of a matrix, don't think chapter 4. Right? And if I say, what's the characteristic polynomial of a differential equation? Well, that's a totally, don't think matrices, don't think chapter 5. Right? So same term, totally different interpretations, but a strong analogy of how they're used. Now, I will do one last little bit of foreshadowing, and that is very hard to see this coming right now. But it will turn out, the very last day of class, in fact, we're going to find that there is a relationship in a weird way between characteristic polynomials of matrices and characteristic polynomials of differential equations. It's really hard to see that coming right now. So anyway, just a little foreshadowing. There is yet another connection there. Okay. Let me remind you of something about characteristic polynomials long ago. This goes back to, let's see, this is page 133. This is long ago. And remember, we made this observation of that there's kind of a wonderful list of coincidences that happen when you're looking at characteristic polynomials of differential equations. And that is, whatever your differential equation is, the order of the differential equation, that's always exactly the same as the degree of the characteristic polynomial, which is always exactly the same as the number of roots that you find. Well, and then we subsequently modify by, adding multiplicities. Which is always the same then as the number of solutions that you get from the roots that you found. And in this context is also equal to the order of the differential equation tells you the grand total, again, loosely speaking, grand total number of solutions you're looking for in your fundamental set. And all of these numbers are always equal in this chapter 4 context, and again, suitably interpreted when you have multiplicities. Okay, so Isn't that a happy little story there? We find ourselves now with a new kind of characteristic polynomial. Characteristic polynomial of a matrix. And look what happened in our very first example. We had a 2 by 2 matrix that gave rise to a degree 2 characteristic polynomial that gave us 2 roots, aka eigenvalues, and which in the sloppy slang parlance gave us 2 eigenvectors. And so we seem like we're noticing gosh, it's awfully analogous. These numbers are always the same. Could it be that these numbers are perhaps always the same? Fingers crossed. Wouldn't that be nice? We almost expect it to be true, just by analogy. Okay. You can probably tell how I'm building up to this. Nope, not true. So heads up, be aware. This is a very tempting allure to think, well, we're calling it characteristic polynomials, and everything worked out so happily in chapter 4. Shouldn't it kind of morally, doesn't it kind of have to work out well in chapter 5? And so be aware, the answer is a resounding no. It just doesn't. This is not a happy little story. This is a frustrating, sad story in that sense. So here is a simple example. And by the way, notice how harmless my counterexample is. Harmless looking. Not scary at all. Ones and zeros. It's a really simple little matrix. And let's play the game. Here's a characteristic polynomial. Multiply it out. Collect terms. There it is, fully factored. You have one and only one eigenvalue. Now, no problem. One eigenvalue. Could still be that there's a two-dimensional null space. Possibly. We're still hopeful. But no. You take that eigenvalue, plug it in the usual way, look for the null space. Here's what that equation turns into, and make your rank argument, blah, 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 and there's one eigenvector. Just the one. And it's not that there are other eigenvectors that we haven't found yet, and we're just, haven't been clever enough, or, there's some complex eigenvectors that, we'll rationalize, later on. No. Only one eigenvector. It's just bad news. Okay, so heads up, be aware. Okay, so here's just another example, just to keep it going. Here's a matrix. Play the game, write down the characteristic polynomial, go through, multiply out, collect terms, factor. You get this. Here's a root with multiplicity 1. Plug in that eigenvalue. You can make a rank argument and justify that you have one eigenvector. Now, the rank argument does change here a little bit. Let's think it through. Let's look at this matrix. What can I say about the rank of that matrix? Wait a second. It's a 3 by 3 matrix at this point, so we've really got to think of this in a different way. We can't just say, it's just like the 2 by 2 case. Now, there's more possibilities here. Now, I do know this is singular, so the rank can't be 3. It's obviously not all zeros, so the rank can't be 0. But that does leave two possibilities. The rank could be 1 or the rank could be 2. The way you're going to resolve in this case, whether the rank is 1 or 2, you have options. My preferred way to do it would be to think about the column space. Look at these 3 columns. More to the point, look at these 2 columns. These are obviously not multiples of each other. Right? Clearly. They're not multiples of each other, therefore these 2 non-zero columns are independent, and therefore the column space is at least 2-dimensional. Therefore the rank cannot be 1. Therefore the rank must be 2. Everybody see how that argument worked? So a little bit of a different twist, but still the point is, by inspection, by casual glance, well, it can't be anything but 2, therefore it's 2. Very convenient. Once you know the rank is 2, you know the null space is one-dimensional. Once you know the null space is one-dimensional, you get to infer any obvious solution you can find is the only solution. Again, speaking casually, sloppily, math slang. Yep. Oh, was that a... No? Okay, sorry. Okay. Does anybody have any questions? Feel free. No. Okay. What about the other eigenvalue? Let's see, for when lambda is -1, that multiplicity was 2. Stick that in there. There's your null space equation. Again, you can make a rank argument here. Let's look at this matrix. What's the rank? The rank is obviously not 3. It's obviously not 0. In this case, I'll make a row space argument. There's only one non-zero row. Therefore, the row space has to be one-dimensional. Therefore, the rank is 1. So again, how you deal with, figuring out the rank might be a little bit different every time, but once you know the rank, then you know the dimension of the null space, and everything sort of falls down from there. So let me flesh out those details. The rank is 1, therefore the dimension of the null space is 3 minus 1, namely 2. Now, when you have a two-dimensional null space, not as nice as a one-dimensional null space. One-dimensional null spaces, find any vector. It's a basis, you're done, right? It's super, super convenient. 2, not quite as nice, but there is still something really nice about two-dimensional spaces. And that is that you can find any 2 vectors that are not multiples of each other. They're independent. And therefore, make a basis. So here you just have to play clever games again. Think about, what can you multiply, what can you dot with that one non-zero row and make 0. And again, nothing to derive, just be clever. Notice that works. That blue dot yellow gives you 0. Analogously, this vector. A different, clever move comparing 2 different coordinates, and it's obviously in the null space. Easily observed, smart alecky observation. So I have found, by hook or by crook, 2 non-parallel vectors, and therefore they span the null space. Everybody okay? All right. Okay. Quick summary. Eigenvalues are roots of the characteristic polynomial. Eigenvectors are in the null space of A minus lambda I. And then one little bit of terminology and notation. That null space we refer to as the eigenspace for that eigenvalue. And this notation here, so E with a subscript, we'll use this sometimes as a nice shorthand. It's just a lot less to write down than NS of A minus lambda I is, clunky. Okay, so how many are you going to find? There are some things to say about this. The analogy with Chapter 4 is not perfect, but it's also not a complete throwaway. Think back to Chapter 4. If you have a root of multiplicity, right? We knew back in Chapter 4 when you found a root of a certain multiplicity, that tells you, in fact, how many solutions, how many of the things that you're looking for you would find. So one might hope something along those lines would be true here. It's not. But that multiplicity does still tell you something. The multiplicity gives you not how many eigenvectors will you find, but it tells you at most how many eigenvectors will you find. So it's an upper bound. That's a hard result to prove. So we're not going to prove that fact in this course. We'll be able to connect it to another fact a little bit later on, but ultimately we're never going to prove this. It's significant effort. What you can prove, and this is an easy one, and I want to encourage y'all to try this on your own, this part of this pair of inequalities that says you will always find at least one eigenvector. And it's just a matter of thinking through and making an argument about what singularity means and thinking about ranks. So exercise for y'all, if lambda is an eigenvalue, then the number of eigenvectors, again, sloppily speaking, the number of eigenvectors you find will be at least 1. Think about how you'd prove that. Don't forget the big idea here. If lambda is an eigenvalue, a minus lambda I is singular. Follow it from there. So make sure you can do this fact. It's not a hard one. Ask in the discussion section if you're not sure where to go. You can ask me in office hours. I think it'd be a good one to make sure you can do. Okay, so there's a nice consequence of this upper bound being the multiplicity, and it goes like this. Let's think about a situation where we have a matrix, and that's a characteristic polynomial, and roots, and all factored and everything. We know the multiplicities add up to the total degree, namely the shape, the size of the matrix. How many columns are in the matrix. So those multiplicities add up to n. Question, what's the most eigenvectors I could possibly find? In other words, in the linear independent sense, how many eigenvectors will I find for the first eigenvalue? How many eigenvectors will I find for the second eigenvalue? Add them all up. Grand total, how many eigenvectors do I find? Well, best case is that I find the multiplicity for each one. So best case, the most possible eigenvectors I can find is where I find exactly n eigenvectors. Now, this is an immediate consequence of the fact that the number is always less than the multiplicity. Okay. All right. Okay. A geometric point of view on eigenvectors. This is just for kind of visualization purposes. Here's this example that we talked about. You'll recognize that matrix. We find the eigenvalues. We found the corresponding eigenvectors. This you can check back in the notes a few pages. This is arithmetic we've already worked out. So what does this mean geometrically? Let's look at this pair right here. That vector 1, -1 is an eigenvector. By the way, don't forget, not only that vector, but every multiple of that vector. All eigenvectors with the same eigenvalue. And the eigenvalue is 4. So what we mean by this eigenvalue being 4 is that the action of this matrix on that vector is to multiply it by 4. So said differently, what this matrix does, the action of that matrix, or you might say, what does that linear transformation do in the plane? Well, that's a hard question, but on this line, it's easy. This matrix does a very simple thing on this line. Everything on this line gets stretched by a factor of 4. That's it. The direction doesn't change. So there's something really interesting about that line. It's preserved by the matrix. Everything on this line just gets stretched out and stays on that line. Okay, and then analogously, this vector, there's an eigenvector. Eigenvalue is -1. That vector is here, right? Well, of course, it's also all multiples of that vector, also still eigenvectors. And what does the matrix do on that blue line? Well, every vector on that blue line gets multiplied by its eigenvalue of -1. So everything on this blue line just flips over. Gets multiplied by -1, in other words. And again, it remains the case that this blue line is preserved. So this linear transformation is kind of a wonky matrix. It's not entirely clear how to think about it. A really good way to think about that matrix is that everything on this green line gets stretched out by a factor of 4. Everything on this blue line gets stretched out by a factor of -1. And everything else does what it has to do by linear combinations. So that's a point of view. And what I have in this next example here, we don't have time to go through, but this is you'll recognize another matrix. Let me do one super quick thing. This matrix, recall, this eigenvalue of -1 had 2 eigenvectors, and that means that this entire plane is eigenvectors. Everything on this plane gets multiplied by -1. Okay, y'all have a good day. See you later.